in a second. Okay, so the final thing I want to introduce, because it's something I'm passionate about and because it's one of the strengths of MATLAB and shows you how you can really play with equations in MATLAB and real mathematics to do some stuff that's very relevant to biology and enables you to do some very powerful things, is this systems biology modeling. So it's what I do, and what I do is I create little systems of equations that represent the way things in our body change over time. So that might be how much antibody is produced by our B cells over time, or it might be how a cancer grows over time or something. So you can represent lots of these things that change, usually over time, with equations, with specifically differential equations. If you've done Calc 101, we're doing the rates of changes of certain reactions over time, or certain metabolites over time, or certain concentrations of things in your blood over time. So this is a really powerful technique to be able to test hypotheses that you might have. So you might be doing a study, you might have found a protein interaction that has never been seen before. You can create a little system of equations that represents that new reaction to test whether the mechanism that you hypothesize is true is really able to explain the data that you're seeing. And it has many, many applications beyond that. But I want to show you how easy it can be and how powerful it is. It's a great way of making data more translatable, because you can create a simulation of your data that's going to be true in all organisms. It will represent the human body, even though you might be doing your experiments in mouse or yeast or something. So it's a very good way of translating your animal experiments up to higher organisms. Okay, so let's consider this very basic little reaction. This is I have to introduce the idea of kinetic rates to you for a second. So if I have two metabolites, I might call these chemical species, using the terms interchangeably. They can be thought of as proteins, if that's how you'd prefer to think. So I have two proteins that are going to bind at some rate to create a complex. So protein A and B are going to bind to create AB. What do we know about this reaction? What do we know about the rate of change of, for example, protein A? Well, we know that A is going to change at a rate proportional to R1. So the faster the reaction goes, the more of A is going to be taken up into the complex. So what determines this rate R1? Well, this is when we begin to use some loose mathematical notation. We know that the rate of change of A is going to be somewhat proportional to the amount of A and B in our system. So if you put a bunch of metabolite 1 and a bunch of metabolite 2 in your system, the more there are, the faster they're going to bind to some extent. There's some, various enzyme kinetic studies in this sort of thing. But in terms of binding, the mass action laws will dictate that the rate of this reaction is going to be proportional to the concentrations of A and the concentrations of B. And so the mathematical way of writing this is that dA dt, which means the rate of change of A over the rate of change of time, so how fast A changes over time, is proportional to the concentration of A and concentration of B. To make that a little bit more rigorous, you can convert this proportionality symbol to an equal sign if you just add some parameter. So it's going to be the rate of change of A over time is actually going to be equal to the concentration of A and B, with some fudge factors, some constant k. And I've put a minus here because A goes down as the reaction goes forward. So the faster the reaction goes, the less A we have, the more complex AB we have instead. Okay, so this is our very basic system, and you can do this for each metabolite in the system, and you get the same equation for everything. So the rate of change of A is going to be negative KAB. The rate of change of B is going to be negative KAB, because for one A going into the system, one B is also going into the system. And then the rate of change of the complex AB is going to be exactly the same but positive. So as A and B go down, AB goes up, and all the mass is conserved. And that seems trivially simple, but this is exactly the sort of thing that builds up to make much more complex systems, and it doesn't take many of these reactions to be beyond intuition and for emergent behavior to emerge from these dynamical systems. So MATLAB lets us investigate this system very easily and create simulations of what might happen in these systems over time. So what we need to do is define a function. And this function has to have a very specific format because we're going to use an ODE solver, which is a differential equation solver, to solve this system of equations. And by solve this system of equations, I mean have a look at what the time course of each of these metabolites is going to be over time. We're going to get out how the concentrations of these things will change as the system evolves. But we can do this simply by defining these three equations. Does everyone follow where these three equations came from? Have I lost anybody at DADT? Okay, awesome. So we have these three equations. All we need to do is put them into a function of this format, and then MATLAB enables us to do all sorts of things with them. So I've created a new function. I've called it odefile.m. It has a function definition at the top. I've called it ODE file, and it has to have these two inputs, one of which is time, and one of which is going to be this x variable, where x is going to be the concentration of each metabolite. So x1 is going to be the concentration of A, x2 is going to be the concentration of B, and x3 is going to be the concentration of AB. So as long as we have this format, MATLAB knows what to do. And it's going to return some delta. I'll talk about that in a second. I've defined it in this layout where I've first defined my k. We know that we need a k. I've made it 7 in this example. You can find these kinetic parameters in the literature and various databases. If anyone becomes more interested in this sort of simulation, I can help guide you in terms of where to find these parameters. Then we know that the rate of binding is going to be K multiplied by the concentration of A multiplied by the concentration of B. So x1 contains A, x2 contains B, and x3 contains this complex AB. So the reason I've defined this binding rate here is because we're using it in every single equation. This has a binding rate, this has a binding rate, and this has a binding rate. So now all we need to do is fill this output with how much these things change over time. So this ODE function has to have this sort of format where it takes time and takes concentrations, and it returns some delta, which is how much these metabolites change over time. I'm going to start with it being zeros. We know that zeros, given some numbers, will define an array of zeros of a certain length. And for this ODE function, we have to have our output the same size as our input. So if we have 3 metabolites in our system, we need delta to contain 3 zeros ready to fill with the rate of change of those 3 metabolites. So that's why I use zeros of length x. X, we haven't given x a value here. It's going to be passed as an input when we call the function. So I'm telling you just to know that x1 is going to be the concentration of A and x2 is going to be the concentration of B. But right now, when it doesn't have any values yet. It's going to get values when we call this function. So we're going to tell it the initial conditions of these metabolites.
So then how do you understand the x parentheses how does it know what x is?
At this point, it doesn't. If we hit run on this, it wouldn't work. It would say, where is x1? But we're going to call it using an ODE solver, and it's going to automatically populate all those values for us.
So x is going to be an array.
X is going to be an array that's going to be 3 big, containing the concentration of A, B, and the complex. And so we define, so we define delta to be zeros of the same size, ready to fill with the rate of change of these things. So then I just define my 3 rates. So delta 1 is going to be minus the binding rate, delta 2 is going to be minus the binding rate, and delta 3 is going to be plus the binding rate. That correlates with here. Minus the binding rate, plus the binding rate. And that's it. We just type end, we're done with our function. So all that function does is define these 3 equations and define and have an output where delta is the rate of change of each of these things. So delta 1 is going to be the minus KAB, delta 2 is going to be the minus KAB, and delta 3 is going to be the plus KAB. Delta 1, 2, and 3. So it's very simple. Once we have that, we're able to do some awesome things. Let me just check if it's on the next slide. Okay, so here's how we run our system. We're going to use this ODE15S function. There are a bunch of other ODE solvers. This one's great, general purpose one, which I use all the time, but I'll let you investigate further if you get more into this. And The syntax looks like this. You know, I screenshotted the MATLAB help so we can see what it's expecting as an input. And it's expecting an ODE function. Well, it just happens that we just wrote one. It's expecting a time span to solve the system over. And it's expecting y0, which is some initial conditions. So how much AB and complex AB is there in our system at the initial point? If we're simulating some reaction in a dish, there's probably going to be no complex, ideally, and a certain amount of A and B, depending on how much we put in. So we solve this system of equations with this line, which I've just covered up. We call ODE15S. We're going to pass it the ODE file. You have to put an @ sign before it to tell it that we want to pass this function in. Most of the inputs that we've used to our function so far have been either numbers or arrays or strings. If we give a function itself as an input, we have to use this @ sign. So we pass it the ODE function we just wrote. We pass it the time. I want to solve it from 0 seconds to 2 seconds. These time steps are pretty arbitrary. It depends on the units of our kinetic rates, but from 0 time steps to 2. And then I've said 0 with a step size of 0.1 to 2. And then I've given my initial conditions to be 1, perhaps those are nanomoles, 1, 0.5, and 0. So there's none of the complex. There's 1 nanomole of A, and there's 0.5 nanomoles of B. And that's it. When you run that, it'll chug away. It'll give you 2 outputs, one of which is time, and one of which is the concentration of all your metabolites. And then you can run plot on T and Y, and you should see how the rates of these things change over time. You should see A and B being used up, and AB emerging from our system. So what does that look like? So it will look like that, where you will have 3 curves from running this. You can tell which is which from their initial conditions. A starts at 1 nanomole, so this is A getting used up. B starts at 0.5 nanomoles, that's starting here, also getting taken into the system. And then the complex AB starts at 0 and increases over time until it reaches an equilibrium where we've run out of B at this time point, and it settles at a steady state of the system here. So we can see how this system evolves over time. I'll keep moving on. I'm sure people are still typing or not getting this to run, but I'll just keep introducing the concepts, and then you can come and talk to me if you want to figure this stuff out. So if we want to, this is how you expand these things. This is a very trivial system, but as I say, all you have to do is just keep adding individual reactions to this thing to represent your hypothesis or to represent the system that you're interested in, and it very quickly becomes more interesting. So this is the same ODE file. What I've done is I've added an extra reaction that represents perhaps the complex A being converted into a new product. So this is a very normal enzyme-mediated reaction where perhaps the enzyme binds to some substrate, they bind together and they process to form a new product. And you would represent it like this. I'm going to need another kinetic parameter representing this rate of R2, and then the rest is the same. Delta is now going to be 4 numbers big because we have 1 more metabolite, and delta 4 is going to go up at some conversion rate, while delta 3 goes down at that conversion rate. The rate of conversion is going to be proportional to K2, which is this second parameter, and also proportional to X3, which is the rate, which is the concentration of AB. So the conversion rate, the rate of this moving forward, is proportional to the concentration of the third metabolite, which we know is this complex, and some kinetic rate K2. And we know that metabolite 3 goes down at that rate, and metabolite C goes up at that rate, which is why we have a minus conversion rate here and a plus conversion rate here. So those are the changes you would need to make to add this reaction. You can then run the ODE solver the same way. Again, the same time points. We need 1 more initial condition now. So we have an initial concentration of A, an initial concentration of B, and 2 zeros for the initial concentration of the complex and C itself. You then run plot Ty on the whole system to plot the concentration of everything over time, and you get something like this out, and things begin to become more interesting now. Again, we can see A going down and being consumed into the complex, B going down and doing the same. AB transiently increases while the complex is first being made, and then begins decreasing as it is being converted into the final product C over time. So you can see how this system is evolving over time, that there's some peak here of a transient concentration of AB. And it doesn't take long, many reactions to add to here to begin to see how things might become interesting. So we've mentioned this as we've been going along, that you can debug your system by adding breakpoints in the corner. So where you see next to these line numbers, these little dashes, if you hit the dash, you should see a red dot appear. So while you're figuring out this sort of stuff, it's very good to add some breakpoints, run your code. It will stop on the line that you specify, and then you can step through line by line, looking at how these arrays are built up. So in this example, I would run my command with the breakpoint on the first line, and it would stop here. What you can then do when your code is stopped with a breakpoint is hover over a specific metabolite, a specific variable, and see its value. So let me just show that over here. If I run this code, stick a breakpoint over here and press play, it stopped here. Now if I hover over X, I can see all of its values. This is very useful when you're debugging. If you're trying to figure out what's going on, hover over X. Let's see, does Y have a value yet? It does. Let's step and see if the value's changed. Okay. And then you can go through line by line, hovering over things, looking at how their values change, and looking at what each command does. So debugging is super useful. So the final thing I will leave for you as an exercise afterwards, if you'd like, is we can combine everything that we've learned here to create a plot representing a parameter scan of our system. So what this code does, briefly, is it creates a figure. We know that if you type figure, now you can create a blank figure ready to fill with things. I'm going to have hold on because I want to add a bunch of curves to this figure. What I'm then going to create is a large empty matrix ready to fill with time courses. So I want 21 time points for my system that I'm solving over time, and I want 21 parameter values. So I'm going to have a look at what effect these different parameters have on how the system evolves over time. This is something we often do. You might want to find out how changing a metabolic rate or adding a catalyst into your system would change the way the system would evolve. It's often used in things like bioengineering. You're trying to maximize the amount of biofuel and minimize the amount of a waste product, or minimize cost, for example. You might simulate the system like this, scan a parameter that you can control, and have a look at what effect that has on the system. So this array of zeros, we know that zeros is going to create a 21 by 21 array of zeros. And what I'm going to do is put the time courses in one dimension and each parameter value that I'm checking in the other dimension. So for I equals 0 to 0.1 to 2, we know that's going to be 0, 0.1, 0.2, 0.3. I'm going to solve my system of equations, but I'm going to make the initial concentration of one of my metabolites equal to I. So the first time, remember the order of these initial conditions is A, B, the complex A, B, and C. So the first time I run it, the initial condition of B is going to be 0. The second time I run it, the initial condition of B is going to be 0.1. The third time it's going to be 0.2, etc., etc., etc. So it's going to solve this ODE, this series of equations, again and again and again, with different values of the concentration of B, the initial concentration of B. So I might be investigating how much B to add to my system in my dish to find out how to maximize perhaps the complex or perhaps the product C. And what I'm going to do for each one of these is plot t versus y. You can leave this out. It's going to create 21 individual plots, which can be messy. They're all going to be on top of each other because we had hold on. But what I really want to do is store all these time courses that we're producing as we go along in this matrix of zeros that we just created. So matrix of time courses, remember it's 21 zeros, 21 zeros. I want to store at the current index, filling the entire column, y3. So what's y going to be? Well, y is the concentration of our metabolites over time. Remember that one of the y's looked like this, another one looked like this. So y3 is going to be the concentration of not A, not B, but the complex AB. So it's going to store the concentration of AB in the matrix of time courses at the current index. So what that means is you might have, if this is our matrix of zeros with 21 zeros and 21 zeros, for I is 0, or do we start with I is 1? For I is 0, we scan I from 0 to 1, but the current index starts at 1. So we're going to store at the current index, which starts off as 1, the time course for the complex AB if the initial condition of B is 0. So the initial condition of B is 0, it's going to solve it, and it's going to store it at 1. So here will be this time course. It will be down here like this. For
You've just done I plus 1.
So the first time it's going to store B equals 0 here, then it's going to store B equals 0.1, and because we iterate the current index equals current index plus 1, and it's going to store that time course here, B equals 0.2, and store that time course here. So we end up with this array of time courses, and that's exactly what we can put straight into Surface and plot it. So we create a new figure, we run Surface on this time course, and it creates a 3D surface where every trajectory is plotted vertically in this space, and we can label the axes with time and the concentration of the complex and how much of the initial B there is. And we see that we have this evolving system where as we add more B, we definitely get more of the complex, but it seems to max out and reaches a peak at different times, and you can investigate this parameter space, etc., etc. So it's great for investigating how a system might evolve over time.
The surface, when you do surface of a matrix,
Yes.
it basically uses
The indexes, yes.
Y.
So there's two ways to run surface. One of them is giving an array of x, an array of y, an array of z. The other way is to give it a matrix of just z values, and it will plot them with the x and y corresponding to the index, 1, 1, 1, 2, 1, 3, 1, 4. And that's what we did here. Okay, so I'm sure didn't follow 100% of that, that's totally fine, but I'll give you the slides and you can recreate those examples and stuff yourself. And if you become interested in this stuff, let me know. So that's the last thing I wanted to cover today. I'm going to be here and around, and if you come up with questions later, let me know. Email me, whatever. My office is just down the corridor. And if you want to keep learning MATLAB, which I hope you do, one thing I will say is that we're thinking of extending this course because there's only so much you can do in 3 days. So we would like to put on a more advanced MATLAB course that continues to create some more useful functions. So if you let us know on the survey that you would like that, that would be great, because then we can have some weight to try and put that on. There is a textbook with a bunch of examples online that is freely available at this link. So if you go to mathworks.com/Mola, I guess, by Cleve Mola, you can skip the first few chapters because we've covered them and continue learning. I have a paper about how to study certain systems with these mathematical models, so I'm going to sell out and plug that too.